Okay, let's get started. I think everybody has joined. So hello, good morning, afternoon, evening. So I'm Kenny Grip. I'm one of the product managers at MySQL, and we also have Miguel Araujo on the call, who's a software engineer at MySQL, and in particular working on the MySQL InnoDB Cluster, InnoDB ClusterSet, as we're going to show today. So today we'll talk about disaster recovery solutions. So about 2 weeks ago, I had another webinar where I kind of introduced MySQL InnoDB ClusterSet, what it is, you can do with it, and so on. And today we want to kind of reiterate some of that and then show quite a lot of the time today we'll spend on demonstrating everything, how it works, how to set it up, and show how easy it is and how actually powerful this is. So maybe, so Miguel is having his slides. Maybe Miguel, if you can do the next slide and the next one. So to start, to like kind of introduce first is like when we talk about disaster recovery, right? So I'll talk more about high availability versus disaster recovery in a couple of slides. But what is still important is that high availability is a kind of a fairly common thing. So basically it's failover, preventing a failure. So when a system fails, when a single server fails, that automatically or manually another system can take over at any time. When we talk about disaster recovery, we're talking about a whole region or a whole data center losing power or going on fire and things like that. And here's a survey from Uptime that shows a little bit what the causes are for these bigger outages, so these disasters, and it seems like power is still the biggest, 37%, as you can see in this 2020 results. This is from 2020. Power is a significant cause of outages. Fire is 0%, although that's not true. I will have an example for that as well later. So next slide, please. Also, what is the cost of a disaster, right? And if we look at the same number, numbers from Uptime, is that the cost over time, so in 2019, the costs were lower than it was in 2020. So in 2020, more than half of the disasters that happened have cost more than $1 million for companies. So that's something that will continue as companies rely more on technology more and more. Doesn't have to be a tech company. The impact is significant. So it's very important to have some disaster recovery process in place to guarantee the business continuity. So here's some examples. So we have the examples: Delta, OVH, AHBC, and British Airways. Fire 0%, while the OVH cloud, remember this was kind of last year, I think, although time, I don't know, 2019 or 2020, one of the cloud's data centers caught fire and had a big impact for a lot of customers, of course, of them, and that cost quite a lot of money for them. Similar with Delta Airlines, where a outage cost them $150 million. A lot of flights were canceled. A lot of people were impacted by this in the coming days because of this outage. So it's very important. So maybe next slide. So now what I want to talk about is a little bit about MySQL and what the past, the present, and the future brings, right? So in kind of the past, but I think a lot of companies are still doing that, is that MySQL heavily used, a lot of companies using big and small deployments, and one of the powerful features of MySQL is replication and the flexibility of replication. So it's very easy to set up your own database architecture with a primary and multiple replicas, and you can have different architectures that suit your specific need as a user, and you can have multiple tiers of replicas where you have a primary and then a secondary, which is also a primary of another secondary, and so on. So there are users of MySQL that have like one replication topology that spans like hundreds of database servers just in one topology. So that is actually quite a lot of users have that. Most of them users have a single server or maybe a high availability or a kind of like a failover setup where there's a primary and a secondary. And what kind of is in the was in the past is that what you have to do to set up this architecture is a lot of manual steps. You have to create users, restore a backup to provision a new replica. You have to configure this replication configuration. And MySQL offered kind of technical pieces to set up this type of architecture. But then it's up to the user to kind of like customize it, make it their own. And a lot of users have their own setup, which is unique, but most of them set up more like a standardized environment where there's a primary and two secondaries, and there's some maybe third-party tools that help, so either open source or proprietary tools that help set up this and manage such an architecture. So there's in the end, it is a lot of work of what the DBA does, or an expert on whatever you want to call it, spends time automating and integrating this architecture into their environment and making sure that it's easy to set up, easy to manage, and so on. So there's a lot of work involved. If we go to the next slide, please. The present is that we, in 2016 at Oracle, we've introduced some new products which we call like our solutions. And the first one that we have released in 2016 was MySQL InnoDB Cluster. And MySQL InnoDB Cluster changes this way that we kind of give pieces of technology to the user and have it give a lot of flexibility to users. That still remains. You still have all this technology, but now you can kind of, we give our users like, okay, a lot of our users just want high availability. So MySQL InnoDB Cluster provides high availability in an easy to use way to set up the whole environment, to do automatic failover and so on. So MySQL InnoDB Cluster is based on using MySQL group replication, which is also kind of released in the same year. And group replication provides an automatic kind of a cluster where you can add and remove members automatically. It provisions the data if there is no data. It guarantees consistency in the event of a failure of a server. So if the primary fails, there's not going to be any data loss. The secondary will take over automatically and will just continue within seconds. There's automatic network partition handling. So if there's a network partition, there's no split brains and whatsoever. So it's very easy. Sorry about this. This is my cat. is quite an active one at times, even though he's 20 years old. So what we aim to do is to make this kind of easy to use as well. And I think what we had here with a lot of our customers and users of MySQL InnoDB Clusters, the group replication is a good technology, it's great with all these features, but also the ease of use is equally important. It's just in a couple of commands, you set up a whole database architecture. This also includes our kind of our MySQL Router, which is our kind of load balancer that provides access from the application to the database, and the router monitors the whole system and redirects traffic to the primary if the primary changes and so on. And it also does load balancing of reads and so on. So everything is kind of fully integrated using kind of MySQL InnoDB Cluster, and the management of this happens through the MySQL Shell, which we'll demo today, definitely. So we guarantee no data loss here in the event of a single server failing, and the time to recover is seconds. So within seconds, I think 5 seconds is the minimum, the new primary gets selected and becomes active. Now in 2020, we introduced another kind of solution, which is similar in terms of like the ease of use, the integration. Actually, the user interface is the same. It's very little difference. And instead of using MySQL group replication as the database replication method, it's asynchronous replication. Asynchronous replication is the default replication, or kind of the replication that's been around for almost 20 years. And we wanted to integrate this as well in a solution just to make it easy to set up a kind of more basic environment, which does not have automatic failover. It does not guarantee that there's no data loss, but it has some benefits in that if your network is not stable, if you have a lot of packet loss, if you have kind of network outages, which some of our users do, then well, asynchronous replication is going to be a lot better. With group replication, you have to have a very stable network. Packet loss will impact the cluster because we have to guarantee no data loss. So we have to do some consensus between, for every transaction between the members to guarantee that they have received it so that we can guarantee no data loss, the split brain prevention, and so on. So Replica set, same kind of ease of use, but with asynchronous replication. Now, this is all high availability. And the next thing that we have that we've released this year is MySQL InnoDB ClusterSet. And this is just kind of an addition to MySQL InnoDB Cluster in that you will use MySQL InnoDB Cluster within a single data center. And you can then add more InnoDB clusters to that one InnoDB cluster and make it a cluster set, so a set of clusters. In this diagram, as you can see here, we have a primary cluster on the left, which is Rome, and then Brussels is a secondary cluster. And they're both MySQL InnoDB cluster. They have automatic failover within the InnoDB, their individual InnoDB clusters themselves. And then there's asynchronous replication between those clusters. So meaning that there's a primary cluster and a replica cluster. The primary cluster gets all the writes, and then that gets replicated through asynchronous replication to the replica. So what we can guarantee in an environment like this is that there's no data loss. So RPO 0 within the region, because that's MySQL InnoDB Clusters guarantees. Failover time will be seconds. But when there's a disaster where the whole primary cluster goes down because of power loss, for example, then you need to fail over to a other cluster. And the disaster recovery, the guarantees are different. So there is no guarantee of data loss, no data loss there. There might be data loss. So RPO is not 0. So we might have, depending on the environment, the network, there's a lot of variables, but you can have a couple of transactions lost, a couple of milliseconds. It could be more if your network bandwidth is not sufficient enough and so on. So there's a lot of impacting variables that determine it. But what we have is no data loss when a single server fails, which is more common than a whole disaster or whole region failing. When the whole region fails, we have some data loss. And then there's a manual failover. However, manual also being very easy. It's a single command to move the whole primary cluster, to promote a replica cluster to become the primary cluster. One big benefit of this is that there's no write performance impact because it's asynchronous replication between regions. And I'll go into that in the next couple of slides. So again, here, its ease of use is very important. You use MySQL Shell. We have full MySQL Router integration, and the router is integrated to understand about the whole cluster set, about the whole topology here, which is in this case 6 database servers. We clone, we take physical snapshots automatically to provision hosts and so on. So all of this is very, very easy to use. And Miguel will demonstrate that today. There's no limit on the amount of replica clusters that you can have, actually. So here you can have 3 clusters, but there's always one primary cluster, and then the other clusters are replicas. So in this case, we added a Lisbon region where Brisbane is a replica cluster as well. There's routers everywhere. So you can have routers in each data center, and we'll talk a little bit more about the features of router and how it helps in configuring and how the behavior works with that. Next slide, please. So business requirements. So I've touched briefly on it, but I want to kind of summarize this and see, is this a good fit for you or not? When we talk about a failure, we have 2 concepts. We have the recovery time objective. So the objective is how long will it take to recover from a failure when it happens? And the recovery point objective, RPO, is that how much data can we lose when a certain failure occurs? So the types of failure are also different. And the RTO and RPO can be different depending on the type of failure. So if we talk about high availability, we talk about a single server failing, a network partition within a data center. So we have RPO 0 in the event of MySQL InnoDB Cluster and so on. When we talk about disaster recovery, it's a full region failure. And that's where MySQL InnoDB ClusterSet comes into play. There's also another kind of failure, and that's a human error. It could be, for example, somebody doing drop database, or a bug in the application where data gets deleted and that gets replicated immediately to the whole database topology. So there's a different type of recovery you need to do. Is you need to recover from a backup, do a point-in-time recovery. That can take a lot longer. The RTO can be quite high on that, depending on kind of what your requirements are. So, but we will not cover that today. So today we talk about high availability and more in particular disaster recovery. So to help you choose on the next slide is that for when we talk about high availability, we have those two choices here. And that's MySQL InnoDB Cluster and MySQL InnoDB Replica Set. So RPO 0 and RTO seconds with MySQL InnoDB Cluster. And with MySQL InnoDB Replica Set, it's RPO not 0, so some data loss is possible, and RTO is how long it takes for you to fail over manually, because there's a one manual command you have to run. So you might ask, okay, InnoDB Cluster is superior. Yes, it is superior, but we still have users of InnoDB Replica Set because of this, if you have a bad network, even so in a way, I have here best write performance is a benefit, meaning that in InnoDB Cluster, every transaction has to be certified by the majority of the members. So group replication uses XCOM protocol, which is a kind of a Paxos-based algorithm. So there's consensus that has to happen for every transaction before the transaction can continue, and it's kind of acknowledged that the transaction can be committed back to the application. So we don't have that with InnoDB Replica Set. So the write performance, throughput, latency will be better with InnoDB Replica Set. Again, a lot of variables, but in general, you could say that. The downside is, of course, that this is manual failover and some data loss is possible. So these are kind of the choices you have. If we talk about multiple regions, if you talk about disaster recovery, so where we want to prevent a failure of a region to prevent downtime when a region fails, we have two choices. And I haven't touched on it yet, but we do have users that run MySQL InnoDB Cluster across 3 regions. So if you spread 3 members or 2 members in each region, so 3 regions, so either 3 or 6 nodes, for example, you can have an environment where there's no data loss when a region fails, and the failover time is seconds. So this will only work if your network is very stable between those 3 data centers. So packet loss will cause network partitions, or if the network goes down for a minute, it will have an impact, of course. So it's very important to run this over the public internet, for example. So you need a very stable wide area network. You need 3 data centers to have automatic failover. It does not work with 2 data centers, because if you want automatic failover and prevent disaster, we recommend within InnoDB Cluster to have an uneven amount of members. And if you put 2 members in one region and then 1 member in another region, if the data center with 2 members goes out, power goes out, then the 3rd member in the other region is there waiting, because it doesn't have a majority. So it needs to guarantee that it can gain a majority before a new leader will be elected there. So what will happen is that no failover will happen to the other data center. So it's going to be a manual action to activate it. Also, because it's a Paxos-based algorithm, we only need the majority of the transactions to acknowledge. We cannot guarantee RPO of 0 in that case, because the consensus can be had in a single region, because it's just 2 out of 3 just need to acknowledge, and the 2 are in the same data center, they will acknowledge and they will continue, and the transactions will happen. So there's no RPO 0 in that case. Another solution you might do is to put 2 members in each data center, but you will have RPO 0, no data loss, but your RTO will not happen. Why? If the one region fails, you lose 2 out of 4 members, which is 50%. In order to have this automatic network partition handling, and you need more than 50%. So that doesn't work. The secondary data center will still wait until it reaches a majority, and it does not. So it will only have 50%. So that's why 3 data centers are really, really important here in order to continue. So it is not a good solution for many because they don't have 3 data centers, not have the network bandwidth, latency, and so on. And that's why we have MySQL InnoDB ClusterSet, which is on the next slide. And MySQL InnoDB ClusterSet, so it's kind of the best of both worlds. We have automatic failover within a region with MySQL InnoDB Cluster, and then we have asynchronous replication between clusters with a manual failover. So RPO not 0, and RPO is kind of manual failover, so minutes or more depending on how you can react to it. No write performance impact within when there's with the traffic between data centers and so on. And this is often for most customers, at least that we talk to, is okay. It's okay to lose some data in this in the unlikelihood that this disaster happens. Although it is possible that it happens, but this is only once in so many years, so maybe some data loss is acceptable. So this all depends on your requirements of the application, of course, in the business, to know if this fits or not. Anyway, a lot of talking, and maybe I should go hand it over to Miguel, which will now give demos. So no, there's not really any more slides, but there's only demo now. And maybe before I start, so what Miguel will show is 3 clusters with 3 members each. So we have Rome, Brussels, and Lisbon, and they each have 3 members. And you can see here kind of how we structured them. So there will be Rome, a host Rome with 3 ports, Brussels, and Lisbon. This is for demonstration purposes. Over to you, Miguel.
All right. Hi, everyone. Let me switch. Okay, let me start Shell. So first things first, let's create the first cluster, which will be the primary in ClusterSet, like you were saying. So let's create Rome. I'm connecting to it, 3331. Okay, so this is nothing new. Using the admin API to create a standalone cluster. It's creating cluster in Rome on port 3331. I'm going to add some instances to it, 3332. Using clone, taking a physical snapshot. This will be really fast because there's the data set is empty. So really fast. Shell takes care of everything, as you know.
Maybe users don't know. Maybe users have not seen InnoDB Cluster, Miguel. It's okay.
Okay, I'm assuming that. So yeah, Shell takes care of everything. It creates the replication accounts. It handles the setup of group replication, configuration options, and whatnot, and creates a metadata schema, and handles it smoothly and in a very easy way. So yeah, that one instance. I'm gonna add a second one.
And can you talk a bit about MySQL Shell in general? Because maybe some users have.
Yes, so MySQL Shell is the brand new, not so new, has some years already, but it's the new client for MySQL, which supports, other than plain classic SQL, it supports JavaScript and Python and has several built-in APIs available in JavaScript and Python. One of those APIs is the admin API, which is the API used to set up, manage, monitor InnoDB clusters, cluster sets, and replica sets. And you have also a plugin framework that you can use in MySQL Shell. You can write your own plugins using Python. It's very extensible, and it's very pleasant to use, I would say. Okay, so I have the cluster in Rome. I can see the status with the 3 instances. 3331 is the primary, and the other 2 instances are the secondary. And now I will set up an account. So I need to bootstrap router. So I'll start up a router instance, and bootstrapping means the router will connect to the cluster, will learn its topology, and will configure itself to be ready to operate in that cluster. So router needs an account. So the admin API has a command to set up a router account, and this will create an account with a minimum set of privileges required to operate in the cluster, for a router to operate in a cluster. So I'll call it router admin. Create some passwords. Done. And now I'll switch to the other terminal and I'll bootstrap. I'll explain what's happening here. I'll call the router application with the bootstrap option, connecting to one of the instances of the cluster. Doesn't need to be the primary, can be any of them. I'll pick the primary here, but for no special reason. I'll create a folder to deploy router. I'll give it a name, and I'll use the account that I just created using the admin API. So bootstrap the router. As you can see, the router opens 4 ports by default. One for read-write connections in 6446, one for read-only connections. This is for the classic protocol, and also for the X protocol, it will open 2 ports, also one for writes and one for reads. Let me start the router. And I will show here the router log. So you can see what router is logging, what's happening. You can see here that the router found the metadata for the cluster ROM with 3 members running in single primary mode. 3331 as the read-write member, the primary, and the other 2 the secondary ones. Okay, so I wrote 2 Python apps using the connector Python just to simulate traffic going on the router. So I'll start this one that I call app read-write. This is sending write traffic to the to port 6446. That is the port that accepts write of router. And as you can see, it's sending traffic to ROM 331. And I'll start here the other app that I wrote using the read-only port of router, and it's doing by default, a router operates in round robin, so it will send the traffic to all the other secondaries 3332 and 3333. Okay, so we have the first cluster up and running, and now the next step is to create the cluster set. So I'll use the create cluster set command. The command is called on an object of a cluster that is ROM, that is that cluster I created. I'll call it cluster set. And the admin API creates a cluster set. We can check the status of it. You can see this is the simple status where the admin API shows the members of the cluster set. You can see here the ROM, the cluster running in ROM. That is the primary cluster. The name of the cluster set. The global primary instance means the primary member of the primary cluster. That is basically the one accepting writes. Status healthy, all available. And I don't know if you notice here, but router is giving a warning saying that the target cluster is now part of a cluster set and that we should rebootstrap. And this is happening because when you turn a cluster into a cluster set, the router settings are not ideal. One of those settings is the TTL, the metadata cache TTL, which by default is 0.5 seconds. And in a cluster set, 0.5 seconds is way too low, because if you have clusters spread out in different regions, that's a very low value. So we have decided that 5 seconds would be a better fit. And the other option is, what was it, Kenny? It was TTL.
So another problem with this TTL of a half a second means that every router will connect to every cluster every half second to the query of the metadata and the status of the group. Yeah. And if we have customers with hundreds of routers that is connected to a single database InnoDB cluster. If we have 3 clusters, that's 3 times the amount. So the routers might overload the database. So for that, we increase the TTL. We don't even increase the TTL. We actually have another feature in router where it does not query for every half a second. It actually has a listening. It's getting notified. So what it does, it's opening an X protocol connection. So we have a classic MySQL protocol and the X protocol, which has also been released since 2016 or something like that. And in the X protocol, there is a feature where the server can notify the listeners in that X protocol that there's a change in topology. So what will happen is the routers in InnoDB ClusterSet by default will use this feature, which is not enabled by default in InnoDB Cluster. So the routers will automatically wait. Instead of polling every half a second, they will poll every 5 seconds, just to be sure. And they also get notified through this X protocol if a topology changed. And that's kind of what the difference is in the router's default behavior.
Yeah, exactly. So you can see here that we also have a command to list the routers that are bootstrapped in the cluster set, and there's a warning here, the same warning saying that the router needs to be rebootstrapped. So let's do it. We stop the router, we rebootstrap using the force option, and we start it back. And now, as you can see here in the log, what Kenny was talking about, we call it GR notifications, and it's here enabling GR notices using the X protocol port. The warning is gone, so we're good. Next, we will create replica clusters. So we'll create two, one in the Brussels and the other one Lisbon. Let's start with Brussels. So for that, we have the command create replica cluster, which needs the connection details for one of the instances on where the cluster will be created. We have this instance, Brussels 4441. We call it Bru. And we'll use clone again to provision data. And here, the admin API is taking care of everything. And it starts, so it creates the asynchronous replication channel that Kenny was describing before. This channel is managed by group replication, automatically managed. It takes care of the handling of the senders that are the instances on the primary cluster and the receivers that are the instances on the replica clusters. And this is automatically managed based on the group membership info. So the channel group replication takes care of the lists of possible senders and the list of possible receivers. And whenever happens a failure on either the sender side or the receiver file side, group replication will automatically reestablish the channel, keeping it always in sync. Other things are done. The admin API takes care of creating the metadata schema. It enables group application member actions. There's one very important, which is the one to ensure that the members on a replica cluster are always super read-only. So they always have super read-only enabled, no matter what, if a failover of a primary happens, read-only will be ensured. And there's another thing that I will talk later about data consistency. Anyway, so let's add more instances to this Brussels cluster. Using clone again. Here you can see in the output that we configure the replication channel. You can see here changing replication source of Brussels to Rome. That is the primary. The channel is always established from the primary member of the replica to the primary member of the primary cluster. Another instance, so we have 3. A second. Okay. Okay, let's take a look at the status of the Brussels cluster. You can probably notice some differences here in the status from the standalone one to this one. Here, there's a cluster role. This is a replica cluster. There's info about the cluster set replication status. It's okay. And we have our 3 instances. You can see here that the metadata server is Rome in 3341. That is the primary member of the primary cluster. You can take a look at the cluster set status. We can see now that we have our primary, Rome, and the Brussels, the secondary. We have an option in status that is extended. And using this, you can get extra information. So this is using the extended one, we can get a joint information of the individual cluster status with a cluster set status. So you can get information of each individual cluster set member with its own members. So you can have the whole information. Using extended 2, you get even more information about the replication machinery, fenced sysvars, lag, and so on. And using 3, even more. So let's create another replica cluster, the one in Lisbon. So create replica cluster, instance 5551. Let's call it Liz. Same thing. As Kenny was saying, we can have, there's no fixed or there's no limit on the number of replica clusters that you can have in a cluster set. So we'll just have 2 here. Let's have 3 members. So we have HA. You can see here on the router log that is getting information about if it router found a new metadata server running in Lisbon, so it's fetching the information. So Lisbon has 2 members, 1 more. Okay, so we have our cluster set with 3 members, ROM primary and 2 replicas, up and running, healthy. And I think we should talk a little bit about operations. Switch over.
Maybe go back 1 slide just to reiterate what we've done. No, the next slide, please. Yes. No.
Yeah.
No, just the demo slide. Next. Yes. Good. No. Sorry. Maybe it's lag.
Yeah.
Screen sharing lag. So yeah, what we did is we created 3 clusters, 3 MySQL InnoDB clusters into 1 MySQL InnoDB cluster set. We looked at the status and we bootstrapped the router. So what we're going to do now is we're going to do some scenarios, right? So if you go to the next slide, I'll show a little bit about this. Is that we have certain operations we can do. We have manual operations like planned things, like I want to change the topology somehow because I want to do some maintenance. I want to change the replica cluster to be the primary cluster because whatever reason, right? So there's many reasons. And we have 1 command to change the cluster itself, set primary cluster. So this will all automatically promote a replica to become the primary. This asynchronous replication channel will be reconfigured, and the routers will automatically learn about this change and redirect traffic to that as well. So if you go to the next slide, is that you can see in purple, the things that kind of changed is that became the primary, Brussels became the primary, and then the router, we have 2 types of routers. We have the routers on the inside, so the ones with the red arrow too, so have target primary, and the other ones have target Brussels. So we'll talk more in the next section, the next demo after this is what are these routing targets. So you can basically configure read traffic to remain local to your to where the router is. So if you have an application, a reporting application that needs to target it's local, so it doesn't need to traverse the internet or the other data center. Go to the other data center to get its traffic, to get its results. It can stay local. Now you can see that router, if it's target primary, it follows the primary all the time, the primary cluster, and that's what sets primary cluster changes, and then the router will automatically follow this, and so on. So I don't know if we go. Is there a next slide or is it straight demo?
Yeah,
Okay.
well, no, it's a demo. Just a note. You mentioned that there are two types of routers, but let's not, hopefully, not confuse people. It's just one type of router. There are what we call policies. So there's a target cluster. It's a policy of router that it's configurable, and we'll show that now in the demo. So let's start by switching the primary of a cluster. For example, we have the Brussels cluster. This one, that is the primary, and we can change the primary instance by doing set primary instance. And let's pick another one. Let's say Brussels.
Is Brussels the primary?
No, sorry, Brussels is a replica. You're right, it's a replica. But anyway, it's something I would like to show. So let's change the primary of a replica cluster to a different one, and Shell will change it, will trigger the actions in group replication to make that happen. And we can see in the status, in the extended one, what I want to show is that, where is Brussels? Here it is. The primary is now the one that I chose to be the primary. And what we want to show here is that the replication channel is now using the source is Rome 331, that is a primary member of the primary cluster, and the receiver now is the new primary in this replica. And this happened automatically, so people don't have to, users don't have to worry about it. It's all fully automatically managed. Now let's change the primary instance of the primary cluster, that is Rome, and let's pick, for example, 3332. The primary is 3331. And let's take a look. One of the things that you can notice immediately is that router now is sending traffic to the new primary, ROM 3332. And we can also see in ClusterSet extended is already here. The global primary instance is the new primary. Here it is. And if we take a look at, this is a lot of info to show in this little screen. If we go up, we can see here now that the replication channel is using as source the newly elected primary. So this is changing primary in individual clusters. And now what Kenny was talking about was the switchover of cluster sets. So we want to switch the current primary ROM to a different one. So let's switch using the CS, our cluster set object. Set primary cluster, let's switch to Brussels. And there's a lot of things happening here in the background. Shell ensures first that we can actually elect Brussels to be the new primary. It will switch the replication channel configuration. It will wait for the transactions to be replicated. It will update the metadata, change the replication source. It will pre-synchronize everything. And then we can see now that Brussels is the new primary. We can see also that the router already adapted. So it's already sending traffic to the, here the primary member of the new primary cluster, that is Brussels, and here sending read-only traffic to the secondaries. So the policies of router, we can check them also using a command on the cluster set objects.
Iterate the slides, Miguel. Yeah. So because we have some slides on the router part. So we changed primaries now, and what we're now talking is the router integration, right? So so router allows your application to connect to the cluster set. So if you go to the next slide, you can see that we have the target modes, as we mentioned, is that the default is follow the primary, and the target mode is primary means writes and reads go to the primary cluster. You can also change the target mode to be a specific cluster. And if that cluster is the primary, it will allow reads and writes to happen and send it to that cluster, which is the primary. If the target mode is a secondary, a replica cluster, sorry, and you can see that here in the Brussels region, there is a router that has target Brussels. So it's the one on the right, the most right router. It will allow reads to go through to the replica cluster, but it will not allow writes. So this application is a reporting application that is connected to it, and it can always read locally. Use kind of a, and then on the other side, you can see on Rome, on the left, you have a reporting application that also has target Rome. There's no writes coming in, but if writes would come in, the writes would just go to the primary in Rome because the target cluster is Rome, so that works well. So you can configure this on a global level. You can configure this per router instance. There's some more settings, which are maybe too detailed for today because we only have like 12 minutes left.
Yeah.
But that's kind of what the router allows you to do. So back to you for the demo.
So let's take a look at it. So using these routing options, we can take a look at the options. So we haven't changed anything. So it's all the defaults. So like Kenny was saying, the target cluster is to follow the primary by default. So let's start by changing the routing policy of our in our global routing policy of target cluster to follow the Rome cluster. That is a replica. That means, like Kenny was saying, that writes won't happen because Rome is a secondary, is a replica cluster. So let's change it, and you can see that its router cannot connect anymore. Writes are not allowed, and the reads are going to the Rome cluster. So you can see here in the routing options that now the target cluster, the global target cluster, is Rome. So let's change the primary cluster to become Rome now. That means that write transactions can actually work now because Rome has become the primary. You can see here the app already showing that. And we can set back our routing option to follow the primary.
So there's a good use case for this as well. And sometimes applications are only active in one region, in the primary region, and if you set them to a specific target cluster, there will be no writes, there will be no kind of split brain. I mean, the cluster is in read-only entirety, the replica cluster, but the router also prevents access there. And if you have an application that only is active when it's a primary cluster, it will automatically, when the primary cluster becomes this other region, then the router will open up the port and allow write traffic to go through. So it kind of serves that purpose as well. If you have needs where you still have to have reads and writes at the same time, you can run multiple routers. MySQL Router is a very lightweight application. You can run many of them. You can run them on each application server as a separate layer and so on. So you can run a router for primary traffic and then one for the reporting traffic, so read traffic to kind of the local, that stay local to where the application is.
Yeah, so let's talk about failure scenarios. Right?
Yes, failure scenarios. So if you go to the next slide, please. Yeah. So what we've shown now is just like, let's do a planned maintenance, change of primary and so on. But we want to demonstrate also like where the primary member of the primary cluster fails. This will automatically be handled. So if you go to the next slide, you'll see that, okay, automatically replication will be reconfigured, a new primary will be elected and so on. If you go to the next slide, the same will happen when we kill that's what we're going to do. We're going to kill. When we kill the primary member of the replica cluster, asynchronous replication will also be reconfigured to the new primary that gets elected. And that's kind of what we're going to demo. I don't know if there's another slide after this. Yeah, another case will also demonstrate that is when the whole data center crashes. So we're going to kill the whole cluster. and then see how everything behaves, how router behaves. So I have this split brain warning here. Now in the demo that we're going to do, power is lost, so there is kind of less chance of having split brain. So there's possibility here in some cases that there's a split brain. It could be that there's a network partition between clusters, and that network, the primary data center is partitioned but not active for the application, or I mean there are a lot of kind of sub scenarios here, and we did build a lot of like a routing functionality in there to prevent this as much as possible. But this is why failover is manual, because you need to do fencing potentially. If, for example, it's partitioned, you need to stop the other cluster first. So there's various ways to do it, but this all depends on your scenario, your use case, and so on. But router still is very easy to use, and we'll always learn about the latest kind of view of the system. We'll learn about these invalidated clusters, which Miguel will demonstrating, and so on. So it's one command instead of set primary cluster, it's force primary cluster. So exactly. Go ahead, Henry.
Yeah, so let's start by showing the crash of the primary instance of the primary cluster. And for that, I just wrote a Shell plugin. That's a very nice feature of Shell. You should take a look at it. You can write plugins in Python. So I wrote one just to help me here, because 1 hour is not really enough time for this webinar. So so I wrote this command, kill primary instance roam, and we'll just using seek_kill to take that instance down, and we'll take the primary down. You can see here already router is failing now. Automatic the group application automatic failover is happening. It's selecting a new primary. It takes some seconds. Router already noticed a change, and the new primary was elected. As you can see, now it's 3331. We can take a look at the status. It's all good. New primary was elected. So like Kenny was saying, it's the replication channel was reestablished to the new primary, and it's all good. You can see that in the extended. So here is the replication channel on Brussels. That is a replica, is already going to the new primary. We can also kill the primary of, for example, Brussels, right? And it's same thing. This one is a replica, and it's a receiver, and the channel will be automatically restored. Let's move on to show actually the full crash of a cluster, because we're getting out of time.
Oh, can you just show it? It should be fine.
Okay.
Status, because it. Yeah. So what we have to do here is create the object again, because the metadata server was killed. So yeah. So in the demo, it always fails. Yeah.
Yeah. So what is it? Okay, Brussels. So the new primary is 4441, and the channel is already using the new primary as source, the new primary of the primary cluster that was elected before, like I was showing you. So this is all automatic. Group application handles this fully automatically. Next, we were going to show a full crash of the primary cluster. So I also wrote a simple plugin to just simulate the crash of Rome. That is our primary cluster. You can see that the router is not accepting any more traffic there. We can now we will now connect to a member of a replica cluster, for example, Brussels, that is still up and running. We can get a new ClusterSet object, and we can take a look at the status. And as you can see, Rome, that was our primary, it's gone. No online members. It's unreachable. And the other two replicas are in errors. The replication channel is in error state, because now the primary is gone, and the cluster set is unavailable. So now what we have to do is to do a forced failover. So basically to elect a new replica cluster to become the primary. So let's do it. Let's elect Brussels to become the new primary using this force primary cluster command. That is the manual step that we were talking about before for the failover. Shell handles everything, ensures the consistency of data, and it will invalidate the old primary. And this invalidation means that in the metadata, we keep track of the view of the cluster. And when we do a forced failover, we create a new view and the old primary gets invalidated. So in case of split brain, the routers know where is the most up-to-date metadata and which is the actual new primary cluster. So let's take a look at the status. Brussels has become the new primary. Router is already sending traffic there. Lisbon is is the replica, and it's fine. There's nothing, no intervention that we have to do here. It's Shell took care of everything. And Rome is the one that is down, and there's here a warning saying the cluster is invalidated, must be either removed or rejoined. What we can do now is to show how would we. So whenever we fixed the power outage or whatever happened in Rome and we get the instances back up and running, we can rejoin that cluster back to the cluster set. So I also have here a command to bring up the instances. So I'll restart the instances that I killed before and wait a few seconds. Okay, so now we can connect to Rome. And we can restore the cluster from complete outage using this command. So group application is gone. It's stopped in all members. The cluster is gone, and Shell has this command reboot cluster from complete outage that takes a look at the metadata and the configuration of the cluster and brings it up online. It's asking if I would like to rejoin the instances that they were part of the configuration because we read it in the metadata. It takes a little bit. You can see here the router has information about the metadata server in Rome has an outdated metadata view. And this means that this one was invalidated, like I was explaining before. So this is complete. We have now our Rome cluster here up and running, and in cluster set, checking the status. Okay, so the Rome is here, but it's not part of the cluster set because it's invalidated. And now we have to rejoin it manually using the rejoin cluster command. And Shell will ensure configuration is reestablished. And here's our cluster set back to healthy state with the 3 replicas. And now Brussels is the new primary. And router keeps operating without any problem. So
yeah, I think this was it. So we handled kind of the failover scenarios, the common ones, and then how to fail over and bring everything back. If there are any questions, so this was it for today. I know we've been going over 1.5 minutes, but if there's any questions, just ask them in the Q&A, and then we'll try to answer them. We'll stay on for a couple more minutes.